Hey everyone, welcome to Blueprint Reading Session 10 video lecture. I hope everybody had an awesome week and you're enjoying the more fall-like weather. If you're looking at your outline, which is on Blackboard for Session 10, we're going to be going over dimensioning with notes, which is basically going to cover a handful of different features on the drawing that aren't standard, linear type dimensions, size and location type things. So there's a handful of those that we're going to cover. They're going to be all from the text in Unit 22. And then we're going to go over section views. We've looked a little bit at section views in the class where we're cutting through a part to kind of see what's happening inside of it. That's Units 26 and 27. We'll be talking about why they're used, how they're used, what they look like, what the different line types are within a section view so that you can understand what you're looking at when you're reading the drawing. And then we're going to jump into weld symbols, talk about what welds are, what their purpose is, and then what they look like when they're called out on a drawing, a new set of symbology for you guys to get familiar with. And much like the machining symbols that we talked about in the last class, we're only going to kind of scratch the surface with the weld symbols because there are just so many of them that it would be overwhelming to try to cram it into 1 or 2 sessions. Learning how to apply weld symbols, what they mean, etc. It could be several weeks worth of lessons. So we're gonna focus on 1 or 2 different types of weld symbols, give you guys the ideas of what they mean, what they would be, when you're reading the drawing, what you could expect this part to look like based on what you see on the drawing, and go from there. And it should give you a good idea of how they're used, and if in the future you want to dive in and look at more of them, that's completely fine. But we just unfortunately don't have the time to cover every single one within the amount of time we have for the class. So we're going to jump in here at the top of the outline. This is an outline that I used from the last semester, and it says, but first, a quick look at tolerance stacking. So we were doing a class exercise in the last class, and we started talking about, what happens, who determines what tolerances should be on the part, and so forth. So we kind of already did the but first portion because we laid out a design where there was a series of holes in a part, and we noticed that if you pushed the tolerances to their maximum, exaggerated of course, that you could end up with a hole that's even halfway off the part or completely off the part. That's the basic idea behind tolerance stacking, that the more the tolerances build up, you run into issues, and that's got to be dealt with from an engineering standpoint, and then also from a drawing standpoint. You don't just want to randomly put dimensions on your drawing that could cause a part to have a hole that's off the edge, like we did in the last class. So we've kind of covered that. We're going to do a dimensioning and tolerancing class in session 12. That'll give a little bit more detail about what we mean by stacking. But for now, we're going to go ahead and dive right into dimensioning with notes. I need to share my screen with you guys. Let's see. We don't want to do entire screen. Let's go here. Okay. Unit 22, dimensioning with shop notes, and hopefully that's what you guys see. Yeah, looks right. All right, fantastic. All right, so the first type of shop note dimensioning we're going to deal with is a process called knurling. It's a manufacturing process where you cut a diamond shaped or another type of pattern onto the material. And if you take a look at page 120 in the text, which we have called up here, so I can just scroll down. Figure 22-1 gives you 2 examples of knurling patterns. In figure A, we have a diamond pattern, like a cross hatch type pattern, and then a straight line pattern displayed next to that. And this is a process that you mostly use in metals, and the most common purpose for knurling, before we get into how we actually look at the dimension of it, is for grip. So you look at the diamond pattern. If you look at A, the picture in A there, and you see that diamond pattern, you may recognize that as kind of being what the end of a dart, where you actually grab a dart if you're playing darts, has that kind of knurled surface on it, and it gives you a bit of a grip on the dart, so it doesn't just like fly out of your hand. The same is used for steps. If you remember, if you're familiar with like pegs on the back of a bicycle, where you would like put your feet, or a person riding on the back would put their feet, those pegs are knurled in order to give a little bit of an extra grip, not so smooth, not so slippery. And that's the idea behind knurling. Now, as far as dimensioning is concerned, if you look over at figure B in this same area, you'll see that there's a 21 pitch called out, and there are 3 basic types of knurl. There's a coarse knurl, which would be referred to as a 14 pitch, far more rough, definitely lots of grip going on. A medium, which is the 21P, which is what we see here in the B, the customary dimensioning example that we're shown. And then a really fine knurl, a 33 pitch, really tight together, not smooth at all, but definitely not as rough as what you would want, like say on a bicycle peg, where you're really just trying to get that grip for whoever's going to put their feet on there, they don't slip off. So when we see this, okay, so we've got a diameter of 1.25. That's our outer diameter of this particular part, and we see that the area that's going to have the knurling on it is 1.75, and then it's shown as a diamond pattern with 21 pitch, indicating that it's a medium knurl. Now the next one over, the where you see 1.75 again down here, they're doing all of the dimensioning in a note. So they're saying it's 21 pitch diamond knurl. So they're telling you that it's a diamond. You don't have to actually put it on the drawing, the hatch itself. You see it's not here, it's not visible here. So they're telling you 21 pitch diamond knurl. So we know it's a medium diamond pattern knurl, and it's on a diameter of 1.25. So over on the left-hand side of example B here, we're using a more traditional style where we give the diameter 1.25. We actually show the diamond knurl, so we don't have to actually type it out on the drawing, but we do give the pitch 21. On the right-hand side is a more doing it strictly with a note, which is kind of the focus of the session tonight, dimensioning with notes. So we're telling you it's a 21 pitch diamond pattern on a 1.25 diameter. So if you see this on drawing, it means what's over here on the left. It's got that hatch kind of pattern. Same could be said for the example in C. We see a pitch of 0.8, so now we're dealing in metric. Same idea, we've got a diameter there, 25.4 millimeters. It's 36 millimeters long, and we can see, we can physically see on the drawing here on the left that it's the straight line pattern. It's it's showing us those straight lines being machined into the part. On the right hand side, it's the exact same thing as on B. We're removing the 25.4 millimeter diameter and we're putting it in the note. We're giving the pitch now in millimeters, not inches, so it's P0.8. It's a straight knurl, so it's giving us that information without physically showing it on the drawing. And it's giving us a 25.4 minimum, basically meaning it can't be any smaller than 25.4 millimeters. And as far as how large it can be, well, there's nothing here indicating that. So where do we go to find out our tolerance values if they're not indicated on the drawing? We go down to the title block and look at our block tolerances for 1 place, 2 place, 3 place decimals. So this is telling us it can't be any smaller than 25.4 millimeters. But if you want to know how large it can be, you would have to go to the block tolerance because it's not specified right there in the note. So knurling, basically putting a grip type surface onto our parts for either hand grip. If you're screwing something in, the head of a bolt could have some knurl, or like we said, a dart, bicycle pegs, etc. And B and C of figure 22-1 shows you how they're indicated on a drawing. All right, so we're going to move along to chamfers. Chamfer is a beveled edge that connects two surfaces. And if we look down at, let's see, figure 22-2, we see a couple different examples of a chamfer. In the very first one there, we've got a circular or a cylindrical part, and we've got a beveled edge on the end of it. Now, a lot of times, parts will have these types of edges machined into them for fit purposes. So if you've got this, we'll call it a peg. This very first one here, we'll call that a peg. If you got a peg and it's going to be assembled into a hole somewhere, for ease of assembly, they bevel the edge here to kind of guide it into the hole a little bit better. And that's typically what an external chamfer is used for, is almost sort of like instead of immediately being like a size on size or a very tight fit, if you bevel the edge, if you chamfer the edge, it enables you to easier assemble the part wherever its mating feature is going to be. And on the opposite end, externally here, or excuse me, internally here, we've talked about these before. They had a different name. They were countersinks. And it's very, very similar to a countersink if you look at the chamfer here, dimensioned slightly differently, but same basic idea. It's basically to bury something down into the part. We've talked about it before, like the head of a bolt, to make it flush with the outer surface that it's going into. But chamfers can be used in that same way. Countersink chamfer for an internal feature, kind of interchangeable as far as the terminology goes, used for basically the same purpose. Now, when we're talking about how we dimension, or what we would expect to see on a drawing for a chamfer, this very first one we'll go back to that we called a peg. 2 dimensions. You're almost, not almost, you're always going to need 2 dimensions to describe a chamfer. First, you're going to want to know how far back from the first surface to the second surface your bevel is going to be. In this particular case, we've got 0.18. So we're going from the front face of the peg back 0.18, and then we're swinging a 30-degree angle and going all the way around the peg to create that beveled or chamfered edge. So this would be one way that you would see it represented on a drawing. We're going to skip the internal and go down here. Another very common way, especially with 3D solid modeling tools like SolidWorks or Pro-E, or I guess even AutoCAD. I'm not really familiar with the way that AutoCAD does its 3-dimensional or solid modeling. But a lot of the solid modeling programs will have a command called chamfer. And you click on the command while you're inside of your solid model, and you pick the 2 surfaces that you want to connect with your beveled edge, and you plug in this value, in this case 1/16 back from the first edge to the second, and then the 30-degree angle that you're going to cut, which is pretty much saying the same thing that we did up here. And then boom, your solid model now has a feature in it called a chamfer with those dimensions. And then when you go over to your drawing side, the 2-dimensional side of the house, which is what we're dealing with in this class, and you actually dimension that chamfer, a lot of those programs will have a dimension option that will give you exactly what you see here in figure 22-2. You would select that edge that's being beveled or chamfered. It would automatically give you the arrow, the leader. It would say chamfer 1/16 by 30, because it references back to that 3-dimensional solid model geometry, looks and sees that you put in a command called chamfer with those values, and then dimensionally can put it onto the 2-dimensional drawing as a chamfer 1/16 by 30 degrees. So these 2 here, these 2 pegs, the first 2 on the left, they're telling you the exact same thing. They're giving you the exact same information about the beveled edge, but just displayed differently. We've got a more traditional style up here with some dimensions, and then down here we're dimensioning it with a note, chamfer 1/16 by 30 degrees. And we'll go over here. All right, so chamfer 30 degrees to thread depth. It's an interesting way of doing it. Basically, it's telling you it's giving you the 30 degrees for your angle off of one surface to the other, but you're only going back the depth of the actual thread itself. So that's going to be dependent on what type of thread you have, how deep the thread actually is. a little bit of a strange way of doing it, but it's not uncommon to see a fastener, a screw, or a bolt have a chamfer on the edge for the exact same reason that we set up here a minute ago for our peg, to help guide it into whatever feature it's being assembled to. If we bounce back up to the internal chamfer, once again, very much like a countersink. In this particular case, it's giving you the outer diameter, the 1.5 inches, and then it's cutting in at 30. Now, if we remember from before, we would say, dimensioning a countersink, we would give the diameter 1.5, but then we would give the overall angle, you know, on both sides, not just one. So in this particular case, if we were calling it out as a countersink, it would be diameter 1.50 times 60 degrees, because it would give you the total opening of that particular chamfer. Here, where we're dimensioning it just as a chamfer, we're not trying to give it any sort of special indication as it's a countersink into a hole. It's giving you the 30 degrees and the 1.5. It's doing essentially the same thing, just presented slightly differently. And then we've got, you know, we're not always working with cylindrical items. Sometimes we're working with square, rectangular, boxy type stuff, and we bevel those edges as well. And in this particular case, we see a note again, 0.25 times 45 degrees. And it's doing the same thing our peg is here. We're going from this surface here, this vertical surface, back 1/4 inch, 0.25 to this top surface, and then we're swinging a 45 degree angle and just chopping it off right there. I think even in your solid modeling programs, you could do that as a chamfer. You could pick those two edges, give the values of 0.25 and 45 degrees, and insert a chamfer at that point too. And calling that a chamfer instead of a bevel is completely fine. You could see that on the drawing as well. So that's chamfers. Grooves are covered in our next figure here. All right, yeah, figure 22-3, just under where we did chamfers. So there's a couple of different kinds of grooves. We've got square, round, and V grooves. And before we jump into how they're dimensioned and what you would expect to see on a drawing for a groove, we can talk about maybe what they would be used for. And one of the most common uses for a groove cut into a part, and again, this is more engineering and not so much drawing related, but just to kind of give you a background so you know why you're looking at this thing. That's helpful sometimes. A lot of times we will install rubber gaskets, circle rubber gaskets, or O-rings as they're commonly referred to, and they would seat inside of one of these grooves. So imagine cutting this groove into a part that you want to then go in and put a rubber ring and have it seat in there. Otherwise, if you put the rubber ring on there, it's just going to roll around. It doesn't have a place to sit and kind of call its home. So these grooves are where that rubber O-ring would call its home. And that would be used in a lot of applications where you want to seal something, either gas or liquid, something along those lines, where you're installing this particular pin or item into an assembly where you need a seal. You don't want water to get out, you don't want gas to get out. So you would cut a groove into your part and then put the O-ring on it, the rubber O-ring, and then that would provide a seal at the assembly level where this is going to be installed. And depending on the type of O-ring, depending on the type of seal, very much drives what type of groove you put into your part. And there's a whole big sheet, as I've mentioned several times. There's so much beyond what we talk about in the class as far as how do you determine, how big to make your groove. If you need an application where you're going to put an O-ring on to keep gas from leaking out of something, well, how do I know how big to make the groove? Well, there is literally, that's all already worked out. The groove size, depending on the diameter of the O-ring, there's equations that get you to how wide and how deep to make the groove so that the O-ring does its job and keeps the gas or the air or the liquid in place and not escaping out into an area that it shouldn't be. Okay, so quick little blab about why we use grooves. So how do we dimension them? All right, so in A, we're looking at a square groove, and we've got two basic ways of doing it. We're saying that the neck is 1/16 wide, which is going to be, the horizontal dimension. We're calling that the neck of the groove. and it is 0.015 deep. And just real quick, 0.015, instead of saying 0.015, what is it? 15 thousandths, 15 thousandths. Sorry to keep bringing that up, but I realize as I've done this class more and more and more, I get into the habit of saying 0.015. And when you're talking shop in an environment where you're looking at drawings and you're looking at drawings with a manufacturing person, or you're looking at drawings with an engineer or a technician, it's very rare that you would say 0.015 deep. You'd call it 15 thousandths deep, and everyone would know what you're talking about. So I try to get that in your guys' head as much as I can. I apologize. I know I say it a lot, or I've been saying it a lot the last couple of weeks. Okay, so that's one way. We could say 1/16 wide by 15 thousandths deep. Over here, slightly different, because this end piece is threaded, which is very similar to the chamfer that we did just a second ago. Once again, the neck, this time it's 1/8 wide, the width, from surface to surface. And it gets cut to the thread depth. So again, you see these dashed lines, and if we remember from the thread lesson or the thread session that we had last time, those dashed lines represent a threaded area. And so in this particular case, it's saying to cut it to the thread depth. So you can kind of see, if you look close there, that dashed line and the depth of our groove are basically in line. So instead of giving it an actual value like we did over here of 15 thousandths, we're telling with a note, we're using a note to say it's 1/8 wide, and you're going to cut it back to the depth of where the thread starts. Round groove in figure B here. In this particular case, the neck, once again, the opening is 1/8 of an inch, and it is 20 thousandths deep. And it's 20 thousandths deep as a radius. So you're going to actually, the point that's the 20 thousandths is going to be sorry, let me back up and say this again. 20 thousandths deep, it's radius, it's a round groove, and the 20 thousandths measures from the outer surface to the innermost surface of the radius. So you're connecting these 2 points at 1/8, striking a radius that goes 20 thousandths deep into the part. I wish I was able to draw on here. That's one downside of the whole Hangout video thing, is I can't really draw on here. Maybe I'll try to figure that out. But hopefully you're understanding what that means. Yeah, 20 thousandths. Let me see if I can zoom in a bit. Maybe it'll help. 20 thousandths would get measured from this surface here, if you can see the mouse moving, to the innermost part of that radius right in there. That would be the 20 thousandths deep. So you've got a 1/8 wide, 20 thousandths deep, and instead of it just being a square cut, you're making a radius, you're making it rounded out. So hopefully that's fairly straightforward. And the last type of groove that we have here, the V groove. And so we've got a note that's letting us know it's a cut groove 60 degrees times 1/16 flat times 40 thousandths deep. Okay, so in order to get all of this to make sense, the 1/16 flat portion is, let me zoom in because it's really hard to see when we are not zoomed in. Okay, so we need to take a 1/16 across the surfaces, cut in at 60, and that's the full angle. Remember up there when we did chamfers, they were just showing you the 30 degrees, and we kind of flashed back to countersinks and said, well, when we do countersinks, we do the entire angle. Well, the entire angle is coming out this way and coming out this way. So from 1/16, we cut in at 60, 40 thousandths deep. So we end up with a little flat area here, and it is what it is after we start out at 1/16, cut in at 60, and then we're just left with this remaining area here after we go in 40 thousandths. It's a little more of a complex cut. Definitely would cost a little bit more to have it machined into a part than the round or the square groove, but serves a purpose depending on what type of seal you need to put on there. Again, more of an engineering thing than a drawing thing, but we're just trying to make sure that if you come across this, you understand what those mean. All right, moving on to keys and keyways. All right, so keys and key seats, figure 22-4 on page 122. So let's just read the description here. A key is a machine element used to connect a rotating machine element to a shaft. The key prevents relative rotation between the two parts and may enable torque transmission. For a key to function, the shaft and rotating machine element must have a keyway and a key seat. We can see that here in figure 22-4, which is a slot in a pocket in which the key fits. The whole system is called a keyed joint. A keyed joint may allow relative axle movement between the parts. And based on figure 22-4 here, we see a couple of different ways of doing the dimensions. The key and key seat would be designated by width and height dimensions, as well as length dimensions when applicable. And we can kind of see that here. So we've got a key seat and a keyway. The keyway is defined by the width and the height. So in this particular case, we've got 0.312 by 0.156 keyway. So that's cut into this part in order to accept our key. The key seat would have the exact same dimensions. And in this particular case, it would let you know that it's 1 1/4 of an inch back from the front face of the part back for the key seat. And here we've got a key, actually, yeah, so we've got the key seat and the keyway. The square key specification could be done in a note here. If you need a key to put into this keyway, we've got 0.312 square key by 1 1/4 long. So it's giving you, they don't really give you a good key drawing, do they? The key is basically just going to be like a square piece. It's not going to be fully square, obviously, because it would be 3, well, actually it could be, yeah, now that I'm thinking about it. 0.312 square, so it's actually just a piece of metal that's cut at 0.312 squared, and it's 1 1/4 long in order to sit actually in that key seat. So the mating part would be specified by these dimensions here. Over here, we've got two different ways of showing the same thing again. A 0.375 by 1/4 inch keyway here. So it's 375 wide. It's 1/4 of an inch tall. And we can see here 1 1/4 would be the diameter plus the height of the key, the height of the keyway. On the left-hand side here, we're doing the same thing. 0.375 by 1/4 of an inch key seat. We're giving it the 1 1/4 inch depth. And instead of calling out the total diameter plus the height of the key, we're just giving you the actual, in this particular case, they're just giving you the actual outer diameter, and then the key seat would be added on top of that. And then the flat key specification here again, if you can imagine that this blue piece that's kind of hatched here is just a piece of metal, a piece of steel, call it steel. The key that would actually fit into that keyway would be designated as 0.375 times a 0.250 flat key. In this particular case, it's not a square. Instead of it being 312 square, it actually does have a different dimension here. So I kind of got tripped up on the first one there. 0.375 by 0.25 flat key, that is 1 1/4 inch long, which is what the key seat depth is here. So, like we said in the beginning there, two mating parts that prevent rotation. We talked about knurling at the beginning. That was a part that's going to allow grip. It's going to put a kind of a coarse or a rough surface on it to allow some form of grip. In this particular case, we're sort of doing something similar. We're mating two parts together where we're locking them in place and preventing them from rotating. And in order to do that, we use keys and keyways. And this is, oh, there's the telephone, yay. In prior lectures, I said you might hear the telephone ring, and there it is. So we're going to ignore that and move on. Yeah, keys, cool. I'm going to go ahead and zoom out of that a smidge so we can kind of get back on track. I did not put in change notes in our session 10 outline, and I really should have, because we should touch on it really quickly. Change notes are basically added to the drawing, and way back when we talked about the revision block, which is in the upper right hand corner of our format, where we would list out changes. The book does kind of a lousy job of doing this, but essentially it's doing the same thing a revision block would do, kind of on a lower end drawing, maybe a conceptual drawing, which is one of the three types of drawings: conceptual, developmental, and product. In this particular case, on figure 22-5, there's two dimensions that are shown in this kind of chopped up view we've got here, and there's a little change block down there, and next to number 1, it says 0.062 added. Now, what do we think that means? Give you a second to think about that. Number 2, the change 2 says 0.062 added as well. Well, without having the change record, which is what we typically have when we make revisions, there's a document that's prepared separately. We talked about this several sessions ago, where the engineer or the manager of the item will say, you know what, I want to do this, this, and this to the drawing, and it gets approved, the changes get incorporated, and that document, that external document that describes all of those changes, follows the drawing for its entire life, basically. This is more of a quick shop note way of doing it. We're saying number 1 here over at this dimension, the 1.562 dimension, had 0.062 added to it. And what that would mean is, before that revision got made, before that change got made, this dimension would have been 1.5 or 1.500, depending on the level of tolerance that you needed. So they added 0.62 to it, and now it becomes 1.562. Prior to that would have been 1.50 or 1.500, an inch and a half. Same for the 2.75. They're consistently adding 0.62 onto the dimensions. So prior to that, and I don't have a calculator in front of me, so forgive me, but it would have been 2.750 minus 0.062 would have been the previous dimension. They added an additional 62 thousandths to that dimension as well. And so if you see that in drawing, typically if you're looking at an actual production drawing, it won't be spelled out like this. Like I said, there'll be a separate document that will give you a little bit more detail in exactly how things changed. But if you do see a change block like this, in a 1 and a 2, either in a circle or maybe in a triangle type of a note, that's what that's trying to tell you. It's giving you information on exactly what changed. Okay, so we're going to bounce to section views, which is units 26 and 27. I'm going to try to get there in my book here real quick. And get there on the screen, because that helps as well. All right. Oh, look, it kicked me out. So let me get back in here. Like I said, it saved my password for me. Okay, so section views. We've looked at briefly what a section view is, but we got to get familiar with some of the terminology and exactly how these things work, so that if you come across them on a drawing somewhere, you know what you're looking at. Basically, section views, as we've got listed here in our outline, section views are obtained by cutting through a part or parts using an imaginary plane, typically to show the inner features more cleanly than through the use of hidden lines. We've seen drawings in our book that have a massive amount of hidden lines on them, trying to show us all these features that are buried within the part. And if it's just a hole or just a cut somewhere in the part and you want to show it with a hidden line, that's pretty clean and straightforward. As our parts get more complex, as we start to have parts that have more features, multiple features in areas that we cannot see, it becomes important to use section views to show those features. So let's jump over to figure 26-1. And that description I gave you used imaginary plane. We used that terminology. And basically a plane is just what you're going to see here in figure 26.1. Ignore cutting plane line. We're going to talk about that in a second. A, imaginary plane cutting through the object. So if you see that blue, imagine it's just like a blue piece of paper that you slice right through your object with, and you say, I'm going to look. So we see these arrows here, but once again, we'll get there in a second. The arrows indicate which way you're looking in, but right now let's focus on that plane, that blue part. So it is imaginary. It doesn't have to be right down the center of a part, depending on what you're trying to show. A lot of times it is, but it's an imaginary plane that we just slice through the item. In this particular case, it looks like some sort of solid, not solid, but rectangular type of a block with at least a hole cut in it. But then when we put our imaginary blue plane through there and chop it, well, here we see a whole lot of stuff happening down inside of there. It gives us a better view of what's happening inside of this block other than just this one hole with a whole bunch of hidden lines. And we're going to see those hidden lines, what it would look like if you just looked at this with hidden lines. It'd be nearly impossible. So cutting plane line, let's go back to that. Let's talk about that real quick. The cutting plane line, you're going to see it on your drawing, and you're going to see it in a couple of different ways, all of which are legit. We'll talk about that in a second. But the cutting plane line represents that imaginary plane, because it doesn't exist. The imaginary plane doesn't exist. So we are going to show where we're cutting through our object on our drawing using a cutting plane line. So if we scroll down, or I'll scroll down, you can just kind of look down in your book. Figure 26-2 shows a bunch of different ways to represent your cutting plane line on your drawing. A is just two larger arrows, and with a hidden line, or it's not really a hidden line in this case, just a dashed line. It's not representing anything hidden. B, letters identifying the section. If you're going to have multiple sections on your drawing, if you're going to cut through you're going to use multiple imaginary planes, multiple cutting plane lines, you're going to need to label them, or else you're not going to know which one's which. It's going to be very difficult to determine, okay, here's a cutting plane line. Where's the view that I'm supposed to be seeing? If you've only got one section view, well, okay, there it is. If you've got 5 section views, it then becomes important to label them. And we do that with letters, typically just in alphabetical order, A, B, C, D, E, etc. And the letters are placed next to the arrows on your cutting plane line. If possible, sometimes that interferes with other views, other graphical representations. If you've got to move the letters around a little bit, that's okay. CAD programs allow you to do that, but it's important to have them there, especially if you're going to have more than one or definitely if you're going to have more than one section view, so that you can identify which one you're looking at. A lot of times you'll have a simplified plane. If you've got a drawing that's very, very complex and you don't want to add a whole bunch of extra lines in here, either the phantom lines that we see in B or the dash line that we see in A, you can simplify it by removing those extra lines and just having the arrows. Once again, you'd want an A or a B or some identifier next to the arrows so that you know which view in the drawing is represented by that particular cutting plane. And then there's also going to be occasions where we have multiple sheets on our drawings, 1, 2, 5, 10 maybe. And sometimes when we cut a section, when we use a cutting plane and chop through, we can't fit that section view, that view that looks internally, on the same page that we're cutting it with. So in this particular case, in D, at the end of our cutting plane line, it's telling us which section it is, AA, which is over here. If you look left, that's AA. If these were Bs, that would be BB, just again labeling them. And then at the bottom of it here, it tells us which page or sheet to go look for it on. So in this particular case, this section was cut. For one reason or another, we couldn't incorporate the section view onto the same page, so we had to throw it over on sheet 3, and we're saying, hey, go over to sheet 3 and look for section AA. There it is. All these ways are very common as you move forward with your engineering type careers and you're looking at drawings. You're bound to run into all 4 of these at some point. So that's the cutting plane line, shows us where we're cutting from. Here we go. So figure 26-3 is that example of what this part would look like if we were to do it strictly with hidden lines. And you can kind of see here, looking down into this end here of our part, just massive amounts of hidden lines that really don't tell you much of anything. Now this was probably a cast part, or maybe a plastic part that was molded in some way. But the point being, it's got a lot of action going on down inside of here. So we use our cutting plane line. We're going to call it AA. It's our very first section on the drawing. The arrows indicate which way we're cutting. So when we cut with the arrows pointing to the left, we're going to use the same exact projection method that we do whenever we put a view on a drawing. So we're cutting and we're looking in. I hope it's really difficult to show you this with a mouse, but we're looking in the way of the arrow. So then we're projecting our view out the same way we would project a side view out from a front view. Exact same way. If the arrows were flipped opposite and they were pointing the opposite direction, our view would be projected out over here. Third angle projection, the way that we've been doing our views in the class so far. So we can see section AA, it's always going to be labeled. If you've got your cutting plane and it says AA, right underneath of the section view, you're going to see section AA or section BB or CC or DD, you know, whatever the label is. Lot going on in there. So section view definitely necessary for that. Now we can see these blue lines that are kind of there, you know, in our section. What are they? Those are called cross hatching or section lines. So if we scroll down a little bit, it is essentially it's the solid part of the material. So if we go, and I apologize, I'm going to go back up here, but if you see, the lines are only outside here. They're not in here where all of this hollow, you know, drilled out holing type stuff is going on. The hatching, the blue hatching, indicates that that's a solid piece of material. You actually cut the material there. It's not hollow, it's solid. So interestingly enough, there are a variety of different hatch patterns, all of which are in every major CAD program. So if you know that you're cutting through a piece of cast iron, it's going to just be 45-degree lines. If you're cutting through a piece of steel, it's going to be 45-degree lines, but you're going to have them kind of coupled together, you know, 2 at a time. Brass, bronze, copper composites, you're going to have a solid line and then a dashed, solid dashed. And then aluminum and magnesium, you're going to have kind of like these tick mark lines. I don't focus on this a whole lot because most engineering drawings that you come into contact with, unless they're showing you something other than a common material like a steel or an aluminum or something along those lines, if they're showing you sand, you know, a lot of times you'll be looking at a drawing that's maybe cutting down into ground because you're putting, you know, you're putting piping in under the ground or something like that. So you're kind of cutting down into the ground and showing a section that way. There are sections for dirt and sand and gravel and things of that nature. And so those are rather important to identify exactly what you're looking at. But when you're talking about materials like steel, aluminum, brass, copper, almost always in engineering drawings, you're just going to see the plain 45-degree hatching that you see here on the left-hand side. It's rare that anyone takes the time and actually puts these hatches in per the material. It's kind of just almost a given. You know, you cut through it, boom, it's some sort of metal. But like I said, when you get into sand, dirt, rock, gravel, things like that, all of that stuff has its own hatch patterns, and those get applied so that it's a little more clear what you're looking at. You don't think you're just cutting through a piece of metal. You know that you're actually down into the ground and you're looking at stone or rock, things of that nature. So hatch patterns, you're always going to see those in your sections for the solid portions. Real quick, because I feel like I'm taking a long time with this lesson. Revolved and removed sections. At the top here, A is a part. It's got a front view, a top view, and a side view, and there are no sections here. This is just the way the part would look if all you did was put hidden lines in it and just used 3 views. So kind of sloppy. Over here on C, we're going to remove the side view here and replace it with a section view. So what we did is we put a cutting plane through our top view pointing to the left, and down here, that's what that cut would look like. So instead of having this messy view here to show the shape, we're using a section view to show the shape. Now, up here, when I talked about your arrows indicating which way you're going to look into the part, well, I said we would project out like we would a side view. So here it is, boom, right on the side. If you see down here, it's not doing that. if we were following those same laws and we had our cutting plane here and we were looking into the left, our section view should sit right here. It should sit right next to it. But in this particular instance, we've run out of space for some reason. We can't fit it there. That's okay. It just needs to say removed section AA. It's not aligned anymore. You need to know exactly which way you're looking at it. The arrows indicate that, but we're not able to place it like we would typically a third angle projection. That's what's referred to as a removed section or an unaligned section. It would not be in line with the cutting plane, the view that the cutting plane was in. So it's removed. It's placed somewhere else. Revolved kind of does the section in place. In other words, instead of putting this I-beam type shape over in a section in a view all by itself, it does it. It puts it right in there and rotates it in place so that you can see what that area looks like. This is not used very often. This is not something that you're going to come in contact with. It can be a little confusing. Sometimes if it's a drawing that's not really giving you details as far as like all the dimensions you would need to make it, maybe it's more just for a visual purpose, you might see a revolved section, but it's really not something you're going to come in contact with very often. On the other hand, a removed section, absolutely, you're going to run out of space to put section views on a drawing, and you're going to have to throw it down at the bottom somewhere. So that is a very common thing. Let's see. I think that's it for section views. The class exercise is listed on the Blackboard page, or I should say on the outline on the Blackboard page, page 147, assignment unit 26A. We're going to switch that over and make it a homework exercise. So please do that. You're going to have 2 weeks to do it, or roughly a week and a half, because we're not going to meet this coming session. We'll meet the following session, so let's have that turned in. I'll put a reminder about it on Blackboard and send out an email. But we're going to move ahead to Welds because this is kind of becoming a longer session. Okay, so we're going to bounce ahead to Unit 31, but I think what we're going to end up mostly doing is working off of some external sheets that I've got prepared, just because I like them better than the textbook. But there are a few pretty decent things in the text as well. So welding. Welding's the process of joining metal parts together, and you're going to run into this kind of thing, or you're going to run into welding and welding symbols on your engineering drawings constantly. Like I kind of said at the beginning, there is just a slew of different welds that you can do, and this page is just a very small representation of all the different symbols that you could come into contact on a drawing that's describing how the two pieces of metal are being joined. This is a lot. There's a lot in this chart, so we're not going to go over every single one because it would take a very long time. And honestly, these charts exist. They're out there. They're on the internet. So if you do end up getting into a position where you're reading drawings and you're like, dang it, I only know one weld symbol because that's all Mike taught us in the blueprint reading class, it's pretty easy to go out and grab one of these and figure out what it means. So again, we're going to do our best to kind of lay the groundwork to understanding what this is, what the intention of it is here. So Unit 31, let's jump in. Again, we're going to learn some new symbols. We are going to primarily focus on the fillet weld. So on your class outline in that chart, second little area there, fillet, that's the one that we're going to focus on the most and try to learn what it means, what it's telling us, things of that nature. So let me call up this sheet. All right. Now your book has some okay drawings. It has some okay examples of welds, but this is one from a textbook that I used, bazillion years ago, and I kind of dig it. I think it's kind of cool. Actually, you know what? This is actually from this textbook. So no kidding. Must have did something different with it here. Okay, cool. Excellent. Your book isn't that bad. Sometimes I really hate this book and sometimes it does a good job, but in this particular case, it actually does a good job. So in your book, which I was mistaken about, page 182. Okay, so how do we call out a weld? What is a weld? What's it mean? If we look over examples of representation and dimensioning, the C column over here, all the way on the right, we're going to see a kind of like an upside down T shape. And we're going to join the vertical piece with the horizontal piece with some weld, and it kind of exaggerated it in the view over here what a gloppy weld would look like on there that would join those two pieces together. But that's what we're talking about. We're talking about taking two pieces of metal, using a welding machine, putting some glop on there. That's a technical term, glop. We're going to glop some weld on there and fuse those two pieces of metal together. So now we have one piece that can't come apart. So we're not putting bolts in it or screws in it. We are fastening these things together for good. So what's that look like on a drawing? Well, for starters, we have a reference line, and the reference line is going to be a horizontal line, and it's going to be capped off with an arrowhead. So let's just jump, because reference lines are kind of boring. Let's just jump ahead. 2. So the reference line is going to go down and have an arrow pointing on the end of it. If we come back over here, if you ignore this symbol here for a second, we've got an arrow and a reference line. The arrow is going to point to the joint that we're going to apply the weld to, or at least we're going to go with that for now. That's going to change here slightly in a second, depending on our reference line, but just let's stick with me. So the arrow is going to point to the joint, and it's going to have a reference line. Now we're going to build onto that reference line with some symbology. If you go down to number 3 on the left-hand side, basic weld symbol and weld side. Now, like I said, we're only going to use the fillet weld symbol, which is, talk about the fillet weld symbol, which is perfect because it's the example that they're giving in this particular chart here. So it actually works out for us. Now, once we've got our reference line and our arrowhead and we are pointing to the joint, we then have to tell the person who is going to join these two pieces of metal together what type of weld we want. That's done with the symbol. In this particular case, it's done with this sort of kind of triangle, like a 45-degree triangle. Let's see, bouncing back over here, going to our chart, we can see all the different types of weld. Fillet weld is that 45-degree type triangle that we've got going on there. So that's what we would want to place on our reference line to let the machinist or the welder know that we want to fillet weld there. Now, it depends, and it makes a difference what side of the reference line we put the symbol on. So if we bounce back over here to the right, we go all the way back up to the top. Now we've got our arrow pointing to the joint, we've got our reference line, we've got our fillet weld symbol, that little triangle there, and it is on the bottom of our reference line. If you come down here, you'll see, whoa, and there it's on the top. What's up with that? The symbol, and we're going to stick with fillet welds. I'm going to keep you saying fillet weld. The fillet weld symbol on the bottom of the reference line indicates that the area that you're going to weld is on the arrow side of the joint. So we can see the arrow pointing right here. If we go over here to our isometric view, that's the side that the weld's going on. It's kind of tough to see, but if you look back here on the other side, there's no weld there. So reference line and arrow with the fillet symbol on the bottom of the reference line says weld right there. Bang, right where that arrow is. If we flip it and we have our reference line and we put the fillet symbol on the top of the reference line, that is indicating that it wants the weld on the opposite side of the joint. So if we look at this isometric view, the arrow is actually pointing here where there's no weld at all, but the weld is along the opposite side. It's on this joint here, not the one that the arrow is pointing to. If you come down, well, what happens if it's on both? Exactly what you would think. That means it wants that gloppy weld, technical term gloppy weld, on both sides of the joint. So, reference line, arrowhead, fillet symbol on the bottom is going to go right to where the arrow is pointing, on the top, the opposite side. If it's on both, it's on both. Just that simple. Moving right along. And this part, let's see, let me, okay, yeah, we're going to stick with this here. Okay, so I'm not going to go deep into this example here because it's a little complicated, but not terribly complicated. But the last thing that we're going to talk about as far as fillets are concerned, we've talked about placing the symbol on the top of the bottom of the line and what that indicates. There are a few measurements here. The one thing that I'm going to focus on, and I'm going to not focus on the rest, and let me zoom in a bit because it's tough to see, is this half-inch measurement that is to the left of the fillet symbol. So now here we go. We've got our same T shape here. We've got our leader, we've got our reference line, and we've got our fillet symbol on the top of the line, which means we're going to weld on the opposite side over here. That's what that means. Now, ignore 1.5 by 5 to 5. Ignore that. Don't look at that. Half inch. The number to the left of the fillet weld symbol gives you the size of the weld. So if we go over here and we look at our weld, we'll see 1/2 inch by 1/2 inch. So it's a 1/2 inch tall and a 1/2 inch wide. It's kind of like a square, but it doesn't fill the entire square out. It's like half a square, which is basically what that 45-degree triangle is indicating. Obviously, the gloppy mess that you see here of the weld isn't a perfect 45 triangle, but that's kind of what that symbol is, why it's shaped that way, because it kind of comes out looking like a gloppy version of a 45 triangle. So in any case, it's a 1/2 inch by a 1/2 inch. So to the left of your symbol is going to indicate the size of your weld. Ignore the rest of it. We're not going to talk about that. So if you've got a fillet weld, got your symbol and it's got the number to the left, that's telling you how large the weld is. 1/2 inch leg fillet weld. Don't worry about the rest. We're not going to talk about it. You're not going to need to know it for the test at the end of the year. The one other thing that I do want to cover on welds, weld symbology. Let's go over to page 183. See, as we go down this chart, it gets more and more and more complicated here with a lot of extra symbology. Not going to do that. Don't have the time. The one thing that we do want to remember, field 8 here, or row 8. Field weld and all around weld symbols. Ignore the field weld, but this circle here that goes from our leader out to our reference line, that blue circle, that is an indication that you are to weld all around the part. That weld is to go all around the joint that you're pointing to. So if we come back over to, let's see, I closed it, didn't I? Yes, I did. Let me real quick rummage through the book and see if I can't find a better example, because once again, the book lets me down. Yeah, all right, let's bounce back over here. Now, if this particular symbol were to have one of those little circles where the leader meets the reference line, that would indicate that the weld would go all around the joint. In this particular case, it's not possible to put a fillet weld on a flush area here, but let's just imagine for a second that we could weld all the way around this part. That's what that circle indicates. So this right here in row 8, you've got that circle around the line there. That's indicating that the weld is to go all the way around the joint. And that prevents you from having to point arrows or put the symbol above and below the reference line and have multiple call outs for one weld, because it is one continuous weld all around the part. You throw a circle there where that leader meets the reference line, and it gives the person the indication that they're to weld all the way around it. So those are the things that I want you guys to take away. Where you put the symbol on the reference line indicates where the weld is going to be. Both sides means you're going to weld them on both sides. I apologize, guys. My dog is barking. 1 second here. I do have someone at the door. You can pause this and come back in a second. Just give me 1 second. Sorry about that, guys. That's the stuff we have to deal with when I record these live and I don't go back and edit them because, yeah, you know, whatever. But had some food dropped off unexpectedly, but it's going to be awesome later. Any case, so just wanted to jump back in here and apologize. Let me go back to sharing the screen. I got to remember where we were. Welds. Yes. I'm going to wrap this up real quick, guys, because I know it's getting long. But fillet welds, once again, the side of the arrow, the side of the reference line that the symbol rests on, please remember what that means. Please remember that the value to the left of the symbol indicates how large the weld is. And finally, that the circle around the arrow means you're welding all around. And that's, yeah, that's the basic of what we're doing there. All right, so let me stop sharing here. And apologies once again for the interruption. I'll have to figure out a better way of doing this than recording it live and just giving it to you with all this crazy dog barking and doorbells ringing. Okay, so once again, we're not going to meet next week. We're going to do another video lecture, hopefully less interrupted than this one was. Please do the assignment that's listed as a class exercise on page 147. I do indicate that there's just a couple of questions to answer, not all of them. It's on the session 10 outline, so work on that. You have a week and a half to do it before we meet again and to turn it in, but it will count as a homework assignment. If you haven't done all of the homework assignments, I encourage you to go back and do them. They should be a lot easier now that we've kind of gone through things a little bit more. Knock those out. They're an important part of your grade, and I would not like to see you not do as well as you can in the class because of the homework's not being turned in. So roll back, figure out which ones you got. I will prepare a spreadsheet to send out to everyone indicating which ones are missing. That way it'll help you a little bit, but that probably won't happen until Monday. But yeah. Thank you very much for attending this video lecture at some point in the next week and a half. I'll shoot you guys an email, let you know it's ready, and I will have the next video up and running on Monday. Talk to you guys soon.